but in this particular math, just how it kind of relates to us and how you'll be seeing it. Exponentials and exponential equations. Sounds scary, but it's not too bad. Then the graphs. So we'll see if we can get done with those three things today.
Oh no, it's going to be in the whole proportionality. Thank you, Cynthia.
One more chair over there. All right. Any particular questions before we jump into anything? Okay. There's a no. Let's start off with proportionality. As you probably remember from your various algebra classes. Worried about math. If y is proportional to x, because everybody got really quiet all of a sudden. Just deep breath. Y is proportional to x. What does that mean for y to be proportional to x? Somebody tells you why, something is proportional to something else.
That means they are related. If x goes up, y goes up.
Yeah.
And opposite way.
Yep. If x goes up, y goes up. If x goes down, y goes down.
Yeah.
Proportionality,
Okay.
yes.
Should I mention the equation that demonstrates this?
An equation that demonstrates this, please do.
Y equals k x, and k is the slope.
Y equals kx, sure, that's a nice way of expressing that. We can say y is equal to k times x, where k is some number.
The slope?
K would be known as the slope, yes. There's another way to express this without k, which comes up a lot. It looks a little more scary, but we can also express this with this symbol. Y is proportional to x.
What's that symbol called?
Proportionality.
Oh.
It just takes the place of the k. It says we don't care what particular k is, it just says y is proportional to x. That means we would know that if we saw this, we would say if x increases, y increases. If x goes down, y goes down. All right. And then let's take a particular example of this equation. How about y is equal to, we'll pick something nice and easy like 5x. Y is equal to 5x. In this case, the k is 5. You would also say that, okay, I know that this is proportional. As x gets bigger, y gets bigger. And now a simple question, when x is 3, what is y? Time's up.
15.
Oh.
15, yes. Y is equal to 15, which is equal to 5 times 3. All right, that one was particularly easy. Not trying to be scary. It gets a little bit harder when we have to turn it around. When y is equal to 3, what is x?
Three over 5?
3 over 5, yes. Here, write it down in a more clear version of this. We'd say that, come on, you can do it. 3 is equal to 5x. And from that, we would conclude that x is equal to 3/5. Any right surprises there? All right, what does a graph of this function look like?
Line, a straight line.
Straight line. Let's see if we can graph it here. Get rid of that function. you go. Straight line. It's also going through the origin here. So that when this tells you that when y is equal to, well, y is equal to 5x, when x is 0, what is y? 0.
Yeah.
So it goes through the origin, and that's just a straight line graph. Nothing very exciting there. All right. And how we're going to encounter this when we get to chapter 9. So again, what we're doing is kind of math, but it's related to stuff in the chapters from 1 through 9. That's why it's kind of bouncing around. Photon absorption, and now that you're kind of aware of what I'm trying to get at here, I'm really trying to only get at the math, is proportional to density. So photon absorption, we're thinking of our X-ray photon, and it's proportional to the density, and this is the density of the tissue. So the density, the more dense the tissue or the material that the photon is trying to get through, the more likely the photon is to be absorbed. Correct?
Somewhat.
Does that make sense?
Density
Can you say again, please?
Can I say it again? Probably not, but I'll try. Photon absorption is proportional to density, so the more dense the material, the more likely the photon absorption is going to increase. More likely the photon to be absorbed. Okay, so let's write this as, we're going to write this as P, and P is going to be the probability of the photon to be absorbed. And we're going to use rho for density. That's the Greek letter, rho is H-O, Greek letter rho. Usually that's what we use for density. B is probability of the photon to be absorbed, rho is the density. So now in our symbols, we're going to say that the probability is proportional to the density. So far so good, dealing with a whole new set of ideas. I mean, it's really just this proportionality, but all of a sudden we have a whole new set of ideas and symbols showing up, right?
New language.
Yeah.
Yeah, it makes it just kind of mucks up the whole thing. Got it. If we could just keep it with the simple stuff, it'd be great. All right, here's a typical sort of question. Think of a substance without having to resort to looking anything up.
Soft tissue?
Well, I'm going to use, I'm just trying to remember a couple of numbers. Let's say, or I would like to use a couple of typical metals. How about copper, which has a density of approximately 9,000 kilograms per meter cubed.
Boo, boo, boo.
How much more likely is a photon to be absorbed in copper than aluminum? And our density of aluminum is around 3,000. I'm going to keep the numbers simple. These are approximate numbers. Kilograms per meter cubed. Also, we have this new idea Density, mass per unit volume. Something that's more dense has more mass in a unit volume. And before we get into answering the question, here's an old trick question. What is heavier, a pound of lead or a pound of feathers?
Pound of lead is heavy.
They weigh the same.
Pound is a pound.
Pound is a pound, yes. So a pound of lead, pound of feathers. But there's something different about a pound of lead and a pound of feathers.
Oh,
It's volume, I'd say.
One's more dense.
Volume.
yeah.
So your pound of lead and your pound of feathers, which one has the larger volume?
Feathers.
The feathers. You're pretty sure about that, right?
Mhm.
Okay. So which one is more dense, feathers or lead?
Lead.
Lead.
Lead is more dense, feathers are less dense, less mass per unit volume. It's kind of a quick idea of just how to think about density. You know, pound of lead and a pound of feathers, they both have the same mass, but one has got a lot more, one takes up a lot more space. Taking up more space means less dense. All right, so in the case of our aluminum, it's less dense than copper. This happens to be around 3,000 kilograms per meter cubed. Copper is about 9,000 kilograms per meter cubed. And let's see if we can answer the question, how much more likely is a photon to be absorbed in copper than aluminum, knowing that the photon absorption is proportional to the density? Well, now we're going to take that expression and we're going to say something like the probability to be absorbed in copper divided by the probability to be absorbed in aluminum is going to be equal to the density of copper divided by the density of aluminum. Scary looking equation. Where did I pull that one out of? Basically what I did is I wrote two of these things down. It's another way of thinking about proportionalities. And notice the important thing, we have probability of absorption is proportional to density. We're going to follow the subscripts here. We got a copper in the upstairs, we got copper upstairs, we got aluminum downstairs, we got aluminum downstairs. And this follows the idea of being proportional to. All right, so the probability of being absorbed by copper divided by the probability of being absorbed by aluminum. We can now put this stuff in, 9,000 kilograms per meter cubed divided by 3,000 kilograms per meter cubed. And we do the math. We notice that the units disappear. That's nice. No units, that's good. A whole bunch of zeros disappear. And we know what 9 divided by 3 is.
3.
There we go. All right. One more step, actually 2 more steps. We're going to rearrange our characters here a little bit. And we're going to say that PC is equal to 3 times P aluminum. This is actually our answer, but we need to put our answer into words. And what are the words for that answer? These are the symbols. This is correct. How do you express that in words? Yes, please.
3 to 1.
3 to 1. I'm looking for some words that would correspond to an answer to the question, how much more likely is a photon to be absorbed in copper than aluminum?
Copper is 3 times more likely to be absorbed than in aluminum.
Bingo!
Sorry.
So we'll put it down this way. A photon is 3 times So it's a little bit of math and a little bit of wording is what we're trying to get at it here.
It mean the copper is more the long time, more than the iron.
Long time?
It mean yeah, it is the copper is more the 3 aluminum is mean the
Well, what the difference is that the copper is more dense. There's more atoms per meter cubed than in aluminum. So the density really has to do with how many copper atoms are in a volume. And so if there's more copper atoms in a volume, then the photons are more likely to hit a copper atom and be absorbed. Okay, so we did what's known as direct proportionality. Let's do another one. Why is So I'm introducing two things in this one. Similar but different. This time there's two different things. Those two different things are, it's now inversely proportional to something. So inversely proportional is important. And I also put a square there. So it's inversely proportional to x squared. And this one comes up so frequently that it actually gets its own name. It's called the inverse square relation. And now we're going to try to put it into some symbols, the way we commonly express it. We would say y is proportional to. And you think you have some idea of what the next little expression is going to be?
K over x squared.
1 over x squared. There you go. That's what it looks like in this set of symbols. Are we happy getting to that point? All right. Another way to write this is that y equals, we'll use k times 1 over x squared. This k just kind of substitutes, the equals and k kind of substitutes for that proportionality symbol. That's all it does. Now let's make up an example. Y is equal to, try to keep the numbers reasonably simple, 2 times 1 over x squared. Now, how do we interpret this relationship in words? As y gets bigger,
X gets
It's mean
exponentially bigger.
X gets smaller.
when let's phrase it the other way around. When x gets bigger, what happens to y?
Gets
It's
smaller.
smaller by
Y
2
gets smaller.
times.
When x gets smaller, what happens to y?
Bigger.
It's bigger.
Y gets bigger. All right. Do you think you can graph this thing?
Around curve.
Something that gets bigger when x gets smaller and smaller when x gets bigger.
Curve.
A curve, yes. Not just any old curve.
Parabola.
Not a parabola.
Half a parabola.
Looks like a parabola, but not. Let's do 2 divided by x. 2. Looks like that function. Let's see if I can load this up. There you go.
No.
So as x gets bigger, y gets smaller, sure enough. And as x gets smaller, smaller means going towards 0 with the origin, y gets really, 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 really big. Now what happens, of course, when x gets negative? Back to our function. If x is negative, is y going to be negative? It's going to be positive. It's not going to be negative. And sure enough, for even negative x, negative small x, y is large and positive. Negative big x, y is small and positive. So this is what we call a graph of 1 over x squared. Actually, it's 2 over x squared, but it's proportional to 1 over x squared, or it is the inverse square graph, as you like. Questions on that graph? All right, let's show you how it's going to show up for us. But before I do that, I want to try to see what this would look like. Y1 is equal to k over x1 squared. This is sort of another particular equation. And I'm going to come up with another one. Y2 is equal to k over x2 squared. Except I lost my k. All right. Happens to be the same character k. And now I have a particular challenge for you, algebraically inclined. I want you to take this equation and divide it by this equation. Take one equation and divide it by another equation. Sounds terrible, I know.
Yes, sir.
You weren't asked to do that in your algebra class. Why am I making you do it now? Because, actually, what do you remember from your most basic sentence in algebra? Equals divided by equals or equals? Sounds like something would be in an algebra class. All right, let's take y1 is equal to k over x1 squared. And what we're going to do is divide this by y2. I'm going to divide this by y2. So whatever I'm dividing by, it's fair, right? Because I'm dividing both sides by the same thing. We agree to that?
Yeah.
Okay, just keep me honest here. And now I'm going to say that this side is y1 over y2. And the other side I'm going to change around a little bit. Instead of writing y2 here, I'm going to write what y2 is equal to. What am I going to write?
K over x2 squared.
Okay, and this is your most terrifying moment. Dividing fractions by fractions. Yes! Invert and multiply. I said invert and multiply, I believe. Sure enough, k's disappear. And we're left with x2 squared over x1 squared. And when they tell you that something is inversely proportional to x squared, y is inversely proportional to x squared, you'll often see it written like this. And you'll have two cases with subscripts. And the reason for this is this gets rid of that constant K, and it doesn't have that weird proportionality symbol. Downside is we got a whole lot more characters to play with. It's always a compromise. Important thing to note here, when you see this equation in the book, in the many places that it shows up, you'll note that there's an expression somewhere in the words he tells you. If he tells you that, notice where the subscripts appear. They switch, right? That's where the inversely proportional is expressed. So, and it's also important, especially with Bouchon. It's like I say, they're working on the 11th edition now, and they correct typos and they introduce typos. And he hasn't always had the subscripts correct. So just bear in mind, whenever you see his proportionality relationships, which he uses a lot, most of them, I'd say 99.9 of them are correct. Occasionally one or two slip in. So you just want to bear in mind that it always has to be checked. Does his words, which are generally always right, match the symbols he's putting down? Just something to keep in mind as you're reading the book. Okay. So the way we typically are going to be dealing with this is the intensity of light. And this is actually going to be the same thing for our photon intensity coming out of the X-ray machine. Our intensity of the X-ray beam, just call it light for the moment, is inversely proportional to the distance from the source of the X-rays. So that means that as you get farther and farther away from the X-ray machine, your intensity is getting weaker and weaker. Sort of reasonable?
Mm-hmm.
Yeah.
Where does